This is a solution for problem number 4 from November of 2009, the Junior Contest on Probability. Consider a quadratic equation, x squared plus ax plus b. If a and b are randomly selected positive integers, such that a is between 1 and 20, and b is between 1 and 20 inclusive, what is the probability that the quadratic is factorable over the positive integers? Okay, so first thing we need to think about is how many different possibilities are there? Well, if I have 20 possibilities for A, and I have 20 possibilities for B, there are 400 unique quadratic equations. But we are asking, what's the probability that the quadratic is factorable? So out of those 400 possibilities, we need to know how many of them are going to be factorable. Now, I think the best way to do this problem is just by brute force. I started by looking at B. So B is anywhere from 1 to 20. Now this problem definitely requires some knowledge of factoring and how factoring works. So for example, if B is 1, that means I have x squared plus ax plus 1. Okay, the only way to multiply to that 1 would be x plus 1 and x plus 1. If this were the case, we would get a to be 2. If b is 2, that means we have x squared plus x squared plus ax plus 2. The only way to get this is x plus 2 times x plus 1, in which case a would be 3. By similar reasoning, when b is 3, a has to be 4. Now the case of b is 4, this is the most interesting so far. So I get x squared plus ax plus 4. Now there's two ways to get this. I could get x plus 2 times x plus 2, in which case a would be 4. Or I could have x plus 4 and x plus 1. Both of these ways I'm going to end up with a 4 as my constant. If I have x plus 4 and x plus 1, that's going to give me an a value of 5. Okay, hopefully this makes sense, but I'm going to go through a few more with us, just in case it doesn't. If b is 5, I get x squared plus ax plus 5. Only way to get that 5 is x plus 5 times x plus 1, in which case a would be 6. Now if b is 6, I have x squared plus ax plus 6. I could have x plus 2 times x plus 3. That would give me the 6, in which case a would be 5. Or I could have x plus 6 and x plus 1, in which case a would be 7. Now what you're going to notice from these patterns, that whatever b is, a is always 1 greater. So when b was 1, a is 2. When b is 2, a is 3. When b is 3, a is 4. So what you can first start by doing is going through and adding 1 to every one. Okay, this last case of 21 can't happen because a is between 1 and 20. Now this should make sense. The reason that a is always 1 more than b, whatever b is, you can always factor to be x plus b and x plus 1. So this case over here, when I had 6, I had x plus 6 and x plus 1. That's how I got a to be 7. Now the interesting cases happen when you have a b that is composite, not prime. So for example, when b is 8, that's 4 times 2 and 1 times 8. 4 times 2 would give me an a value of 6. For 9, I have 1 times 9, which is 10, and I have 3 times 3, which again will give me a 6. For 10, I have 1 times 10, which is 11, and 5 times 2, which is 7. Similarly, I'm going to get 8 and 7 for 12. I'm going to get 9 for 14. I'm going to get 8 for 15. I'm going to get 9 and 8 for 16. I'm going to get 11 and 8 for 18, and I'm going to get 9 and 12 for 20. Okay, we're almost done. Now we need to count up how many different ways is this. So looking at your A column, This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So 34 out of my 400 quadratics will be factorable, and this is going to simplify to 17 out of 200.